In the present video, we're going to study or demonstrate the production of Lewis fractal and dragon curves. We have this worksheet that includes the Levy's fractal. It's in the lower's book, page 46, figure 319. Basically, what it is you start with a rectangular shape and then you transform this by tilting it by 45 degrees and duplicating that side, and it starts building a fractal out of that. The program that does the fractal is shown in here, and it has a parameter p, and we're going to see how far we can go in terms of those values of p. Start with p equal 2. We're going to try to turn 2 to 9. For p equal 3, we took those rectangles, tilted them 45 degrees, and duplicated it. And now we're going to do the same at the next level, which produces this version of the curve. The next one produces a more complex version. Number 6 even more. Number 7 gets more and more complex. Number 8, oops, sorry. And for number 9, of course, it's going to take more time because you're using more memory, and you get that result. I actually was able to get it to m equal 10 and obtain this particular curve, which is all based on that original rectangular shape. And actually for equal to 2 is when we will start and build it up into more and more complex rotations and reductions until you start producing those details that eventually turn into this Lewis curve or Levy's curve. The next example I'm going to talk about, it's called the dragon curve, in which the program is shown in here, and also you can download it later on. It's based on the level of the fractal and an angle in degrees, which the textbook by Lewis recommends to be 90 degrees or higher. In P take up to 11. Of the value 11. This is presented in the book in page 51, figure 323. And here's the program. And when I do, I produce this matrix called dragon, which goes up to level 8 with a degree of 100 degrees, and it produces this dragon curve. And I calculated the minimum and maximum value of the two columns just to give me any idea of what values of x and y we're going to need for my graph. If I change to 90 degrees, then you get a bunch of rectangles, but the curve is based on this more rectangular shape, but it still has that characteristics of extending around the plane and self-similarity that characterizes fractals. So we tried an angle of 100 degrees, an angle of 90 degrees, and an angle of 120 degrees right here. Again, the same kind of meandering curve, but which is called a dragon curve. Now what I'm going to do, I'm going to try to get what happened when we have a, I'm going to copy these and insert it in the next page. We're going to change this to 110 degrees, and it probably won't take that long to produce, but you see the curve slightly different. I'm gonna drag it and enlarge it over here. The same idea, kind of a meandering, self-similar, but it has a different inclination as we change the angle of the angle of of the lines. So let's see what happens if we get 150 degrees here. I'm going to have to pull that curve down this way and reduce the size. Then we get kind of like the path of a river, for example. I suppose that if we try 180, we're going to get some sort of rectangularity to it. Let's see what we get. I haven't tried before. Well, it's just a straight line. That's amazing. All right. So I'm going to try a number between 150 and 180. Let's try 175 degrees. Let's see what we get. So it seems that as we approach 180 degrees, the line starts getting closer to a straight line. Yeah, closer to a straight line. And then the farther away we get from 180, then we get the meandering dragon curve. But as the smaller the angle, we had to recalculate the whole thing in here. There you go. So you get in this meandering curve, but it becomes more and more rectangular as the angle gets closer to 90 degrees. We're going to try now. Again, this you'll be able to download to play with it. We'll talk to the next one, which is Dragon 0. Here's the program that produces it. And this one has a fixed angle. And basically it's the rectangular shape. This is for level 8. This is for level 12, which is the more complex one. If we try smaller values here, like Dragon 6, for example, then you get less and less complex of a curve. Dragon 4. And we got Dragon 8 here. That's the one that's going to take a little bit longer. Oh, there it is. And Dragon 12. This one, I have a picture shown in here because it took a while. So if you download this file and play with it, you'll be able to obtain this dragon curve at level 12. But it's going to take some time to produce it. So after you download it and play with it, this is present in the Levy's book, page 51. And I recommend this values of P of 6 to 9, although I was able to get it to 12, but again, took a while to produce. The problem is that you get more and more points to take care of, and you start taxing the memory in SMath Studio. So let's try the last case, which is Dragon 1. Okay, Dragon 1, it's a little bit more complex programming because it rounds up the curve, and so you start getting this result for Dragon 10. All right, so let's try some smaller values to see how it progresses. If you try Dragon 2, you get just like one bend of the meander. Dragon 3, Dragon 4, Dragon 5, 6. And it's not taking too long to calculate. 7, 8. That one, okay, it took a little bit longer, but not exaggeratedly long. 9. That didn't took too long. And this is 10. This is going to take a little bit longer, but this is the result that you get. So it's a curve that tends to fill the plane, has self-similarity, and in this case, the corners are rounded, and so you get. You imagine you get such a complex path for a river, for example. That will be like a terrain that's full of little cones. Anyway, this is Dragon 1 for the P equal 10, and this is the end of the current presentation on the Levy Fractal and Dragon curves.